we've had lots of examples of these cases where the limit exists and the limit does not exist, because we want to be careful. But what's nice about continuous functions is that the limit would exist everywhere. So we want to look for these scenarios where we have a continuous function. So a function is continuous if it does not have any holes, jumps, or breaks. So if we have a nice continuous function, then when we go to evaluate the limit, we can just use that direct substitution because we don't need to worry about the limit not existing. So what we're looking for is functions that do not have holes, jumps, or breaks. The easiest way to remember this is the idea, can you draw the function without ever lifting up your pencil? So you start at the furthest left point, go to graph it. You should be able to graph the whole thing without ever lifting up your pencil. And that would make a function continuous. So let's talk about these three functions down below here and the types of functions that we're seeing and how that links to the idea of continuity. Now with these, we're looking at the limit as x approaches 2 for all of them. So what we could do is talk about being continuous at a point, and then we can talk about overall continuity as well. So let's focus on this idea of being continuous at a point. If we're trying to evaluate whether or not the function is continuous at that point, all we need to do is use that direct substitution to see if our function's defined there. So the limit as x approaches 2 of x cubed minus 4x. So what we can do is try to evaluate this. So we're going to go 2 cubed minus 4 times 2, which is 8 minus 8, which is equal to 0. So because we got something defined out, we got this value of 0. This means that our function is continuous at x equals 2. So let's take a look at our graph just to confirm this. We could also do it with a table, but let's just go for a quick little graph here. So I'm going to grab my graphing calculator and we're going to look at x cubed minus 4x. So to know that this is continuous at x equals 2, there we can see our coordinate 2, 0, which is defined. And we can see as we approach from the left and the right, we're matching up right there. So that limit makes sense of getting that y value of 0 out. Now this function right here, this is a continuous function everywhere. So this is a cubic polynomial. And if I started graphing this, I'm not going to come across any holes or breaks in this graph here because it's just going to be defined absolutely everywhere. So this function right here is a cubic polynomial. And really it's continuous everywhere. So we could look at the limits absolutely everywhere and it's going to be defined. And that's going to be true of polynomials in general. Just any sort of polynomial, those are continuous functions. Very nice to work with. Now with these, we're going to look at some rational functions. So let's go ahead and try direct substitution. So limit as x approaches 2 of x minus 4 over x plus 3. So we're just going to go 2 minus 4 over 2 plus 3, which is a negative 2 over 5. So we get a value out, it's defined, so that tells me that this is continuous at x equals 2. So at that point, it's continuous, it's defined. But let's go ahead and take a look at this graph because this right here is a rational function, which rational functions are not continuous everywhere. So if we go and plug this in, so x minus 4 over x plus 3. If I tried to graph this, I could put my pencil down and we'd have this increasing part, but then eventually I would need to pick up my pencil, jump down. So we have this vertical asymptote at -3, which is causing a break in our graph. So because of that break, this is not continuous at x equals -3, where our function would be undefined. So we would have some issues there because of that. So rational functions would be not continuous everywhere. But at x equals 2, it was fine. All right, what if we had x minus 4 over x minus 2? So if I try direct substitution, we would have 2 minus 4 over 2 minus 2. So we'd have a -2 over 0, which is undefined. We cannot divide by 0. So this is not continuous at x equals 2. It's going to be because that's the spot where we have our vertical asymptotes. This is another rational function which is not continuous everywhere, specifically at that vertical asymptote. Sometimes they have holes in them too, so we just want to be very careful with our rational functions. We saw it with our square root functions. Pretty much polynomials and linear functions, those are going to be nice and defined everywhere, but a lot of other graphs will have holes and jumps that we need to be careful of in terms of continuity.